So this is part 2, which we're calling the information representation, and we're going to look at the signals and number systems that are involved in digital systems. So signals are generally information variables that are represented by some physical quantity. So those physical quantities may be weight or height or length or distance or speed or simply counting some pulse. And for digital systems, as opposed to analog systems, the variables take on discrete values. So whilst in the real world, everything is analog in nature, it's continuous. For digital systems, we need to discretize these analog signals into digital signals that we can use in our digital system. The most prevalent values in digital systems are two-level binary values. So that is simply 1 or 0, or that is maybe the words false or true, or the symbols F or T, the words low or high, L or H, or the words on or off. And these usages, these words and symbols, will be used throughout the course and will be synonymous with each other. So these binary values, as we mentioned before, are actually representations of some sort of continuous physical quantity. And since we require values to be discretized, so a signal example over time is as time goes along, then we may have some discrete pulses or clock ticks. We have an analog signal being continuous in both time and value. So therefore we can have any value up here, not necessarily just discrete steps, although in the picture it's discrete steps, and then any time value as well. So we don't necessarily discretize it into small steps. In the real world, if you zoomed in further and further and further, there would always be some sort of continuous change between. Whereas a digital system has discrete values in both time and value. So these discrete values are, for example, high or low, or maybe we call this true or false. And then we also have discretized times. So these could line up with the times, perhaps these pulses here. And then this is synchronous signal. And then we also have asynchronous signals. And where it's asynchronous, it is still discrete in both value and time, and it's still also only happening at certain intervals, not completely continuous, but it's not synchronized by a specific clock. It's externally synchronized. So an example of this may be a keyboard, where the keystrokes are not necessarily happening at certain time intervals, but happening asynchronously. So here's what I mean by digital signals that are representing a physical quantity. So the quantity may be a voltage, for example, and say, for example, that we're going to call any voltage that's a value of 1 to be high, and any voltage that's a value of 0 to be low. But in actual fact, since this is a continuous system, in reality, there's going to be some variance on that. So it might be slightly higher than 1 volt, or slightly lower than 1 volt, or might be slightly higher than 0 volts, or slightly lower than 0 volts. So we need to have some sort of tolerance there. This tolerance depends upon the system, but it may be all the way, for example, down to 0.6 volts may be acceptable. From 1.1 all the way down to 0.6 is considered to be a high, and then from negative 0.1 volts all the way to 0.4 volts is considered to be low, and we would call this in-between area the threshold region. So this is sort of a no man's land between the high and the low. If the voltage is sitting in this state, we either have to make a decision that it's high or low, or we just consider that it's the previous state. So in this case here, we're close to 1 volt. It's going along. It reaches 0.6 volts here, and we can either say as soon as it gets below 0.6 volts, then we're going to call that a low, or we're going to continue it being a high value until it gets to the next threshold value, which in the second case here is 0.4 volts. And we could say, so this is all high until here, and then it drops. Our digital system interprets that as dropping to a low. We cross over the 0.4, but we don't quite reach the 0.6 until here, and so we go up to high here. And therefore we have just discrete values. We have this being a 1, and we have this one being a 0, and this one being a 1, And so this is the binary model of the time-dependent voltage for this particular case. In terms of the information representation, we can use number systems to represent that. So this would be a positive radix positional number system. So a number with a radix r is represented by a string of digits like this. A, n-1, the n-2, all the way down to the first and the 0th, and then -1, -2. And so we say that the value ai, for any of these ai values, greater than or equal to 0, and it's less than the radix. So maybe an example would be the decimal system, numbers 1 to 10, and we might have a number like 123.45. And so in that case, all of these numbers, 1, 2, 3, 4, and 5, is all less than the radix 10 because it's decimal system. So we count from 0 to 9 in decimal system. And we also have put it together in such a way that the decimal place breaks up between whole numbers and fractions of numbers. So we have a 1 times 10 to the 2. If we counted it to the left this way, we'd have the 0th, the first, the second, and this way we have the -1, -2. And then we can put this together in this way, 1 times 10 to the 2, like this. The number ai, so for example, where I is 2, then ai is 1, and the radix is 10, and I is 2. So we have 1 times 10 to the 2 plus, then ai, where I is equal to 1, is 2. So 2 times 10 to the 1 plus 3 times 10 to the 0, because this is the 0th value. And then for the decimal part, which is the plus this, we go from -m, so from the -2, and this should be j, so the -2 is 5 times 10 to the -2 plus 4 times 10 to the -1. And all that would give you 123.45. So here's some number system examples for the decimal case and the binary case. So decimal case is obviously you're familiar with this, where the radix is 10, then r to the 0 is 1, r to the 1 is 10, 2, 100, 3,000, and so on. And then r to the -1 is 0.1, to the -2 is 0.01, and so on like that. Then the binary case, maybe you're familiar with, maybe not so much so, but in this case where the radix is 2, so radix 2, to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and so on. And then where the radix is 2 and the radix powers are -1, -2, -3, then it's 0.5, this is a half. Might be easier to look at it as 1 on 2, and this one's 1 on 2 squared equals 1 on 4. This is 1 on 2 to the 3, is 1 on 8, 1 on 2 to the 4, 1 on 16, and 1 on 2 to the 5 equals 1 on 32. So let's have a look at this example here. We've got the decimal number shown by having the radix in the bottom right hand corner here of 10,101. So how many numbers are there here? To the left of the radix point, which in this case is also the decimal point. So if we have the decimal place there, we count 1, 2, 3, 4, 5, and this is the 0th, this is the first, second, third, fourth, and then the m, so how many numbers to the right, then there's 0, and the radix is 10, and we get that from this value here. So we could represent that as 1 times 10 to the 0, plus 0 times 10 to the 1, plus 1 times 10 to the 2, plus 0 times 10 to the 3, plus 1 times 10 to the 4, which if you add it all up would give you 10,101. Okay, so let's have a look at the second example. So the difference between the first example and the second example is the radix. So we've got 10101 and the radix is 2. So this is the one that changes. So we'll once again use this summation I equaling 4, from I equals 0 to I equals 4, AI times by, this time the radix is 2, so 2 to the I. Once again, there's no digits to the right of the radix point, so m is equal to 0. And we can go through. This will give the value of this binary number into decimal. So the first one being 1 times 2 to the 0 plus 0 times 2 to the 1 plus 1 times 2 to the 2 plus 0 times 2 to the 3 plus 1 times 2 to the 4, which gives 1 plus 0 plus 4 plus 0 plus 16 equals 21, and this is in decimal. Okay, and then for the next example, we've got the number 110.101 in decimal, and the number of digits to the left of the decimal place is 3, 1, 2, 3, and these are the 0th, 1st, 2nd, and the number of digits to the right is also 3, 1, 3, and this is -1, -2, -3. And the radix again is 10, the same as the first example. So we can represent this as 0 times 10 to the 0 plus 1 times 10 to the 1 plus 1 times 10 to the 2. And then different to the first two examples, we actually now have a sum between j equaling -m and j equaling -1 of aj, rj, which equals, we've got 0, 10, and 100. And then we've got the decimal place values of 1 times 10 to the -3 plus 0 times 10 to the -2 plus 1 times 10 to the -1. So this equals 110 plus 1 on 100 plus 0 plus, 1 on 1000 plus 0 plus 1 on 10, giving the answer that we originally started with. And then for the final one, we've got the same digit values, but the radix being 2. So this is a binary value. We're going to change this to decimal. Once again, we have 3 digits to the left, 3 digits to the right. Difference is the radix is 2. 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus, let's put the decimals in there as well, 1 times 2 to the -3 plus 0 times 2 to the -2 plus 1 times 2 to the -1, which gives 0, 2, 4, 1 on 8, 0, 1 on 2. So equaling, well, this is the same as 125, this is the same as 0.5, so that we get a total of 6.625 in decimal. There are some special powers of 2 that are often used in conjunction with the term byte, where byte means 8 bits, and especially in Windows operating system to talk about storage capacity. Kilo meaning 1000, but it also is 2 to the 10, so not exactly 1000 when we're talking in digital systems. This is in the range of what a digital floppy disk were. Then we have mega, as in megabyte, which would have been perhaps the storage of an old CD, 700 megabytes, or 2 to the 30, this number here, which is gigabytes. Something like a DVD might have been 4, Blu-ray, USB flash stick, getting to the tens or hundreds of gigabytes, and then 2 to the 40, which is terabytes, more like the storage of a hard drive.